Good morning, distinguished session chairs, honorable committee members, and esteemed delegates of the 2026 International Conference on ICT for Smart Society. My name is Aulia Yunika Butar-Butar, and I am joined today by my colleague, Nicole Alexandra Wang. We are speaking on behalf of our team from the School of Computer Science at Bina Nusantara University in Jakarta, representing all the co-authors of our study titled Bridging Bioinformatics and Dermatology, a computational framework for kinetic-tuned formulative design. Over the next few minutes, we will walk you through the development of Barrier, an AI-based system designed to shift cosmetic analysis from superficial visual pattern recognition to underlying biochemical evaluation. All right, most AI skin tools today only focus on the surface, analyzing photos for wrinkles or uneven textures. Well, while helpful, this is purely descriptive. It tells us what is visible, but not what is actually happening at a biochemical level. Because of this, a product might simply pass every visual check, yet actively disrupts the enzymes responsible for rebuilding your skin barrier. A photo simply cannot catch that molecular interaction. The pharmaceutical industry solved a similar problem decades ago by using computational screening to predict interactions before anyone steps into the lab. However, cosmetic formulation still largely relies on costly trial and errors. When we look at the current landscape, it's hard to find an existing framework that connects skin enzyme kinetics with cosmetic ingredients compatibility. That is the gap we are addressing today. With Barrier, we adapted a computational architecture built for general biology, and we fine-tuned it specifically for the skin, layering on pH awareness and strict dermatological constraints to predict how ingredients will actually behave on your skin barrier. Now let's talk about the mechanism. Our frameworks operates through four main stages. First, we pull out our baseline data like protein sequences, chemical structures, and kinetic parameters from validated public databases like UniProt and PubChem. That data will then be fed into our adapted ENZClip dual encoder architecture. We modified this from previous research done by Khan et al., which was originally designed for general enzyme kinetics. We used this to predict our baseline molecular interactions. Next, we then applied a pH-aware adjustment layer. This step is crucial because skin pH varies naturally, and enzyme activity fluctuates right along with it. Finally, all of these calculations lands in a single barrier compatibility score. Now let me walk you through how each of these pieces work. Data retrieval is pretty much straightforward, but on the other hand, the processing phase is considerably more complex because a single encoder cannot process both protein sequences and chemical structures efficiently because they use entirely different grammars. Our dual encoder architecture solves this by assigning specialized models to handle what they do best. Protein sequences are fed into ESN2, an 8 million parameter model, while the ingredient's chemical structure, which is represented as a smile string, goes to ChemBerta, a 77 million parameter model. Both outputs are projected into the same space and fused using cross-attention. This ensures the final representation captures the actual molecular interaction rather than just stapling two separate summaries together. Out of that, we get the predicted kinetic values, KCAT and KN. KCAT basically tells you how fast the enzymes work once it's got the ingredients, while KM tells you how easily it grabs the ingredients in the first place. Other than those, we also get a raw compatibility score, but we don't just take that raw score at face value. Now here's something that we learned. Enzymes are not equally active at every pH. They follow a bell curve around a specific optimum, and that curve is rarely symmetrical, meaning an enzyme might tolerate an acidic shift much better than an alkaline one, or vice versa. Take GBA1, an enzyme critical for ceramide production. Its optimum is around pH 5.0, right where healthy skin sits. But if you push the environment towards the more alkaline pH of dry skin, its activity drops off fast. We built this biological reality directly into the framework. To do this, the system calculates an activity factor by applying an asymmetric Gaussian model. This measures the exact deviation between a specific skin profile's default pH and the target enzyme's optimal pH, accounting for those different directional tolerances. Finally, we layer physiological skin condition modifiers on top of that. For example, the dry skin profile doesn't just change the pH. It inherently cuts GBA1's baseline activity down to just 0.6 times its normal rate. So now, how do we make sense of all these variables? Well, we multiply them all together. The baseline affinity, the pH activity factors, and the skin modifier. We do this to get the final adjusted compatibility score. For individual ingredients, a score under 0.4 means it is incompatible. Between 0.4 and 0.65 is moderate, and anything above 0.65 is considered compatible. But we don't evaluate a product in a vacuum. We group the enzyme interactions into three functional pillars: barrier integrity, healthy exfoliation, and antioxidant defense. So, compute a specific pillar score. The system aggregates those compatibility scores, scales them by the ingredient's concentration, and applies a 130 multiplier to map the result on a standardized scale from 0 to 100. Now, something's off. We have to consider what the product is actually built for. Because here's an example. A single scoring formula would unfairly penalize an exfoliating toner for lacking barrier repairing ceramides. Or, on the other hand, penalize a barrier cream for lacking exfoliants. So, we calculate an overall score by multiplying each pillar score with their designated intent weights, hence the picture on the very right here. And finally, we added one strict biological safeguard on top of all of this, grounded in a dermatological principle called corneotherapy. This principle dictates that barrier function must always come first, and everything else is secondary. So if the skin's barrier health is already poor, the system forcibly caps the entire score at 50, no matter how good the rest of the formulation looks. By that same logic, the system also applies a heavy penalty to any exfoliants detected on an already compromised skin profile. Now I'll hand it over to my colleague to discuss the result of our findings.
Okay, now let's talk about how we trained the model. So we ran NZClip for 68 epochs using just over 12 million parameters and reached a final validation loss of 1.4421. But honestly, these numbers matter less than how we actually use them. The AI model doesn't get the final say. Its raw output feeds into our hybrid system, which is strictly controlled by real pH behavior, specific skin condition, and corneotherapy rules we mentioned earlier. So, in short, the model gives us a prediction, but biology keeps it in check. Next. To make sure our system wasn't just picking up random, meaningless pattern, we tested it on three cases that reflect real clinical conditions. So first is niacinamide targeting GBA1 on dry skin at pH 6.0. The score came out to 0.461 or moderate. This matches what dermatology research already tells us that GBA1 struggles to produce ceramides on dry skin. Second, phytosphingosine targeting ASAH1 on sensitive skin. This score 0.573, also moderate, which lines up with the well-known ceramide imbalance seen in sensitive skin. Third, salicylic acid on oily skin at pH 4.5. This one's interesting because two things are working against each other here. The pH isn't ideal for calcase-7 enzyme, which slows it down, but oily skin naturally boosts calcase activity to make up for it. Our model captured both effects and landed on moderate score of 0.640. All three cases match what we expect biologically, which tells us the model makes sense from a scientific standpoint. Now let's zoom out. So we model 5 different skin types, each with its own baseline barrier, compatibility score, and enzyme behavior. So dry skin turned out to be the hardest condition for barrier-focused products, mainly because its higher default pH of 6.0 makes it even harder for ceramide-producing enzymes to work properly. Oily skin keeps a fairly strong physical barrier with a baseline score of 70, but it show much higher calcase 5 and calcase 7 activity, meaning there's already a lot of natural exfoliation happening. Sensitive skin actually gets the lowest overall baseline score at 35 out of 100 because both its exfoliation process and its barrier strength are compromised at the same time. To see if this framework actually works outside of a spreadsheet, let us show you a quick demo. We ran a real commercially available product through Barrier. Surface Blemish Control Gel. So as you just saw, the system gave it an overall score of 41.9 out of 100, placing it in the use with caution category. But the pillar scores are what makes this interesting. Barrier integrity score high at 84, healthy exfoliation was moderate at 33, and antioxidant defense was 0, simply because we don't have those specific ingredients in our database yet. This result is actually a strong win for the framework. It correctly identified this product as a gentle, barrier supportive daily formula rather than a strong exfoliant, which matches exactly how Cerafy is marketed. And we got that just from analyzing the ingredient list. So to wrap up, let's talk about where this framework stands today. We're confident in our biological foundation. We prioritize barrier health above everything else. We calibrate our pH models using real skin conditions instead of lab-only data. We treat exfoliation as something that's only safe under the right conditions, not something universally good. That said, we also want to be upfront about our limits. Right now, barrier is proof of concept, not fully validated tool. Our data set is still small with just 30 enzyme ingredient pairs, and our validation so far relies on comparing results to existing research plus one real products case study. So we haven't run wet lab experiments yet. So going back to our main question, can cosmetic ingredients be screened computationally the same way pharmaceutical drugs are? Our early results strongly suggest that yes, it is possible. Our next steps are clear. Grow the data set beyond this. First 30 pairs, benchmark our systems against existing molecular docking methods, and most importantly, run real wet lab validation. If that goes well, we believe this framework could be an important first step, one that helps the skincare industry move away from the expensive trial and error and toward formulation that's actually based on how ingredients behave in the skin. Thank you to the session chairs, the committee, and everyone watching today for your time and attention. My team and I are looking forward to hearing your thoughts and answering any questions you might have.